So we were talking about until now these three steps: creating the mesh, creating simulation parameters, and post-processing, little bit of running. Now, what we will be looking at is basically customizing simulation run. How? So as you know, we can do Python or C++. The maximum flexibility is in C++. These are the environments which we propose. If you are gonna work with Kratos, but there may be some other ones which I'm not familiar with. Yeah, okay, but these are the ones which I use basically. VS Code is my best friend basically, but some people might use the MSVC. Fine. And we use the GDB, which is a GNU debugger, to debug Kratos code. Because what we do is numerical method development, so we always have to debug. We just don't use Kratos, we just make like extend the features of Kratos. For post Paraview, Xterm is used for basically MPI debugging. Like if you are working with some distributed memory architectures, then you want to debug. It's not so straightforward. So for that we use Xterm.
Suneth, the mic is muted. Suneth, can you hear me? The mic, if you can hear me, the mic is muted.
Yeah, sorry. Yeah. Now you can hear me, right? I think. Yeah. I don't see my mic going. Oh, yeah, it's going up and down. Yeah, fine. Yeah, sorry about that. Yeah. So the main topic of the afternoon is understanding data structures and algorithms of Kratos and seeing how we can kind of do what we want. So first thing, there are few levels of Kratos. So we were discussing the first level, VS Code, GID, Salome, Siemens NX. So the easy level. All of these provides input to the Python along with JSON and MDPA or Medfile in the Salome case. Then the Python execute Kratos utility files or whatever the methods which you want to use in Kratos. Then Kratos generates output which can be interpreted from any of these. That's what we did until now. So what's happening in this red box? Basically, you have a lot more other stuff happening in there because Kratos is connected with a lot of other, I would say, technologies. Like I said, OpenMP and MPI, shared memory, distributed memory, HDF5, which is one of the data storage mechanisms for big data, which Kratos supports. You can write and read those things from model parts or the meshes, geometries, everything to back and forth from HDF5. MMG is one of the free, nice like measures which can be used in Kratos also. You can check it. It's from a different repository. We just link it with that. So you can create your own custom measures and then you can do local refinements based on some scheme. I mean, like, let's say that you want to refine where your gradients are wrong. You can tell it to the MMG saying my gradient in here is having this much error, reduce it, somehow refine it like that. So MMG is like that. There's many more of these technologies, which software for the software relations in Kratos. And the structure. Kratos Multiphysics has a core, which we call the kernel. Basically, it doesn't have physics at all. It has interfaces, data structures, algorithms, which are physics agnostic. That's how we keep it always, because we don't want the Kratos Multiphysics core to have any physics. Then in the core, you have here data here, so data containers, numerics, like schemes, variables like this. And you have the applications. The applications also, there are two types of applications. One is called utility applications. Other one is called non-utility applications. What do I mean by that? Utility applications means still they don't have any physics, but they are coupled with third-party libraries. Big libraries like HDF5 is a big library, third-party library. So and MMG is a separate application because it's a big library which we are coupling. We don't want to have the dependencies in the core to these external libraries. Then the non-utility applications are the ones with physics. Like we have structural mechanics, fluid dynamics, core simulation, and then MPM, convection diffusion, a lot of applications. Chimera, those are physics-based ones. So those are that is the basic structure, but it's not. So there are some other subcategories like research applications and stable applications, which we will not discuss here. Yeah, that is like top level structure. Then the usage of Kratos has its own different flavors. One can use it as a tool. That's what we did basically in the morning session. Post processing, custom calculation with small code snippets like that. Just using it as a tool. The next one is development. That means how you can change Kratos. It can be either at Python level. So you can change your Kratos multiphysics Python scripts if you like. Create your own simulation. Or at C++ level, which requires the compilation. HPC level means high performance computing level, where you need some additional information and knowledge also to do that. And then to run the simulations, you can use either it as a CFD solver or computational fluid mechanics solver or particle mechanics solver, something like that. So different flavors of the Kratos. Let's see. Okay, there's a one which this should be removed basically, but yeah, fine. So how Kratos is doing FEM? As I told you in the the morning, so we had the structural mechanism analysis. I told you that's the main execution point Python file which we use in Kratos. So that is a, a specification of the analysis stage. I would say derived version of the analysis stage. First question, do you all know about object-oriented programming, like concepts, right? Then when I say derived classes, you understand what I'm saying. Yeah, okay. So the structural mechanics analysis is a derived class of analysis stage. Because whenever we want to run something, we usually derive from the analysis stage in Kratos, even though if we want to customize also. It has these three methods. Whenever we call run, which we did in the morning session, we call just run. It calls three methods in the analysis stage, which is first is initialize, then the run solution loop, and the finalize. These are the three methods which it will call. Initialize, as the name says, just do initialization. Maybe your variables, reserving some memory for the degrees of freedom, like then assigning the equation IDs so that you can do the global assembly, local assembly on all those things. Run solution loop is looping over time. If you have transient simulation, it has first loop, which is the looping over time. Then it's nested or looping over elements to calculate the local elements, stiffness matrix and mass matrix and everything. Inside the local elements, you have Gauss point loop. So if you're concerned about the efficiency, you need to be really careful about what you put in the Gauss point loop because this is the nested, like lowest most loop you have. So if you put really expensive stuff in here, so your whole simulation will be super slow. So that's why we always have to be careful when we are dealing with in any numerical code. It's the same basically. It's not specific parameters, to be honest. Yeah. Looping over the Gauss points. Yeah. So this is what's happening in the Kratos run solution loop. First, we initialize every solution step. In here, solution step is a time step. Then what we do is we predict the solution which might be true or false. We just try to predict so that we are close enough to the actual solution. So our linear solvers have easy time solving it. As you know, if you are close enough to the solution, like if you know almost exactly the solution, it's easy for the any inverse or the iterative methods to get the actual solution. So predict is supposed to do that, get to the closer to the solution, but it cannot get the exact solution because then it's the solution there. Then you solve the solution step iteratively for nonlinear ones for each time step. This is once you solve, you have some finalization. That means you update your material parameters or some things like that, like the constitutive matrix variables. You just update them, and then you output. This is output is maybe the one which we showed VTK for paraview, for GID, like output in the fields, whatever you chosen. You keep on doing that until you complete the total time. Yeah. So this is the task of the analysis stage. So now let's see the data structures in Kratos, which I briefly introduced in the morning, but didn't go into details. Let's look at this problem. So you have here thermal problem where you have 0 Kelvin, 0 Kelvin, 100 Kelvin, 100 Kelvin. You want to need a see actually how the temperature distribution in this problem. Nothing else. No heat flux, nothing. I'm keeping it simple. So how do you start in Kratos? Morning, I told that model is the top level data structure which you always have to have. It has all the information about your FEM problem. Not even FEM, actually in the optimization case, it will have the whole information about the optimization also. Like model is the main big data container in Kratos. Everything is sub part of it, part of the model. So this is the model. So this should include everything like the boundary condition, everything should be included in the model. So how do we do that? Let's assume that you have two different material parameters for this. One may be aluminum, other one may be steel. Who knows? We don't care. Just an example. So then you need to have two model parts. Referring to those are called model parts. Different domains, different model parts. The model parts can be volume domains or line or the surface domains or edge domains or point domains. It doesn't matter. It's just separate domains. That's what it matters. So you have here model part 1 and 2. Then you have submodel parts. Submodel parts are usually explaining the boundary conditions, but not always. So for model part 1, you have three submodel parts explaining bottom, left, and top. For model part 2, it has its own submodel parts, this. Like that. The submodel part 4 can be repeated in both. It's up to you how you design it. You will see when we do the Python coding. You can design however you like. But one rule is whatever you have in submodel parts should be in the parent model part. It can only be a subset, remember. So if you have here nodes, like say that 1, 2, 3, 4, 5, the submodel part cannot have 10 for this one because it doesn't, the parent model part doesn't have 10. So it needs to be always a subset. That rule is critical. Otherwise, we lose a lot of functionalities which are provided by Kratos because those are assumed whenever those functionalities are used. It needs to be always submodel part. It says that it's subdomain. Then in a submodel part or in a model part, you can have elements. So element can be something like this. In each element, so it can be here like a quad or a triangle or a hexahedron, we don't care. So it will have different types of elements. For each physics also, we need to have separate model parts for each physics. Think of a situation where you have, I don't know whether how you are familiar with fluids. I'm not sure. Okay, because only example comes to my mind is fluid. Yeah, example is basically you can have the same domain with two physics. Like think of assume that your momentum equation is one physics and continuity equation is a one physics for the time being. We don't separate them usually. Then you use both of them in the same domain, right? To solve a fluid problem. So you need to solve the momentum and the continuity mass continuity equation. Both needs to be solved. In that case, momentum equation is a one physics, so you will have one element type for that. That means it needs one model part. Continuity equation is another physics, so you need a separate model part for that. So that's another way of separating model parts. It's not only domains like saying steel and aluminum, but in some cases we use it to separate the physics also because since Kratos is multiphysics. So there's multiple ways we differentiate these model parts. So elements have properties like conductivity for the thermal case. So they can have properties, material properties basically. Then you have another concept called conditions, which are only present at the boundaries. They always share nodes with some elements. Those are to represent the boundary conditions. They can be Neumann boundary conditions or Robin conditions, basically. So it has a contribution to the system matrix. The conditions can also have properties like convective heat transfer coefficient if you are having a flow around this one, or roughness in the fluid case, because the wall roughness basically defines your turbulence in the fluid cases. So they can also have everything. All of them basically has nodes. Yes.
Does the mesh between two different model parts need to be conformal? Does it depend on the simulation?
It depends on the simulation, because if you do multiphysics, you don't need to have always conforming meshes. That's why we have a mapping. Then that's a separate application called mapping application, which does, if you don't have conforming meshes, they do the mapping somehow, mortar or nearest neighbor or whatever. So it doesn't need to be conforming. If it is conforming, it's faster. Otherwise, you pay the price. Yeah, it's always. That's not free lunch, basically. Yeah. So that's the nodes. So we were talking about this, the basic structure. Now let's see what are the data containers. So all of these model part, submodel part, element, properties, conditions, nodes has something called non-historical data value container. That means any of these containers will have a method called set value and get value. So you can set your random values also there as a data holder. I will cover that in the code also in the Python example, just giving you heads up. And it has a flags container saying true or false, because sometimes we need to have this kind of fast access to the true or false to be efficient. As I told you, we are a little bit concerned about the efficiency of the Kratos. Flags container is saying whether this element is active or inactive is an example. Because in some of the examples which I showed in the morning, you saw that there were these two rotating these things. I can show you again. Yeah, this one. So these two rotating things. So here you see this is one mesh and there's a background mesh. So this is map meshes to two meshes overlapping. In there, what we basically do is we activate and inactivate elements, because one mesh is basically solid, other one is fluid. So you, whenever you have a common area, so you activate one of the physics. So like that. So in order to be fast, do that in efficient manner. So we use these flags. This is one use case only, not only use case. Yeah. Then we have an additional container for nodes only, since this is a finite element code, historical data value container. That means only at the whatever the values you stored at nodes, you can access the previous time step values. But that's only available at the nodes. Only others have just one storage. If you overwrite it in the current time step, so you lose the previous time step values. It will always overwrite. But for the nodes, if you write in the current one, but you can still access the previous one also. Maybe the previous velocity example or previous displacement to calculate some time integration schemes. So like that. So only nodes has this historical data value container. Now let's look at what are the variables which I'm talking about. This is the discretized, spatially discretized, and actually temporally also discretized version of the PDE. Whatever the PDE you will be looking at, I think you can simplify to this mass. See, some they call it convection matrix, or in the structural they are calling it damping matrix. It depends on what context you are coming from. C can be D in structures or C in fluids. It's how you come from your background basically. K is stiffness matrix and F is the force. So you have this, and what we are calling as variables is basically x double dot is the acceleration, x dot is the basically one example is velocity, and x is displacement. If you are solving for fluid structure problems. If you are solving the thermal problems, okay, this can be temperature and temperature rate. It depends on the variable. So you have here velocity. Yeah. So the types of the variable which we have is basically we have scalar variables like pressure, distance. Those are scalars. And we have vector variables with components. Let's say that if you work velocity, then you can have velocity x, y, z components also separately, but they will be scalars. Velocity is a first order tensor. Velocity x is a zero order tensor, like a scalar basically. So those are called with components, the vector variables. And one other pointer is, it's not a mistake that I put everything in capitals, uppercase letters, because Kratos variables are always uppercase. It's by purpose so that you understand, even though it's like streaming out your stream, it's purposefully done to actually say that it's a variable, nothing else, always uppercase. So you can have acceleration, force, so like that. Then you can have second order tensors also, like nodal inertia tensor. It has xx, yy, xy, z, like all those things, subcomponents of a second order tensor. Yeah, so those are the with ones which have subcomponents with the names exactly. But there can be second order tensors like the stress vector, which is basically a vector but doesn't have subcomponents. So you cannot ask from Kratos with vector 0, vector 1. Here pk2 stress vector 0, vector 1, like that. It's not there. Subcomponents are not named. You can get the subcomponent by looking at the index, but you cannot directly ask like in here. In here, if you say from Kratos, give me velocity x, it will go to the correct velocity and we'll get the first component. So that flexibility is there. But if you don't have the subcomponents, you cannot access them with a name. Then you have the matrix variables also, like with and without components for sure, like that. Those are the variable types which we have in Kratos. Maximum type at the moment is matrix. Yeah, but I will tell you how to deal with higher order tensors like fourth order, fifth order tensors also a little bit in a advanced session afterwards. Yeah. Then you have elements and conditions. So first is elements and conditions are only working on the local level. They don't know anything about the global system matrix or nothing. It just always whenever you develop your own element also, you just have to think in the local. How would you do your PDE for one element? That's all you have to think in Kratos. Rest is automatically handled. If you do it correctly for one element in your local space, that's it. That's how Kratos is designed. That's why we have from each element these three methods: get values vector, which gives this x; get first derivative vector, which should give for that element the x dot, the whole vector for every node; and get second derivatives is this one. So these are there. It also has these methods, but not only these, there are a lot more other methods to get MCK. So K and F is given by calculate local system. Because for static and transient cases, both need K and F, so we have one method for that. Then for transient only, we have additional methods like calculate mass matrix, or here calculate damping matrix. It's not conversion, it's damping matrix called actually in Kratos. There are a lot more other methods also, which is not included in this course, but you can just check it in the element.h later. Next, there's something called schemes. What is the purpose of scheme? As you know, computers does not understand what is this double dot or single dot. No, they don't understand anything basically unless we tell them. Yeah, the computers are becoming smarter, but still don't understand that. Yeah. So we need to tell what is this x dot means. That means we need to tell some time integration scheme, saying how to calculate x dot from x. The basic one is x dot n plus 1 equals x n plus 1 minus xn divided by delta t. So that's the basic way of calculating that time integration. So this is the purpose of schemes. Those are called time integration schemes. So it converts this information into a delta xn equals bn minus this. This actually is residual formulation. Yeah, something like this. Because remember, computers, it doesn't matter how smart the computer is, they can only solve kx equal f. That's it. They cannot go beyond that at this moment. I don't know in the future, but not yet. So we need to simplify everything to kx equal f at the end. It doesn't matter you have time integration. It doesn't matter how complicated your code is. It doesn't matter you do multiphysics. Doesn't matter. Simply, we need to always simplify to kx equal f. That's what the scheme is, because it knows relationship between x double dot and x dot. So somehow it does some things and then produces a k, which is this in here a, and delta xn equals this is the residual formulation. Basically, that's it. Yeah, so the time integrations can be Bossack time integration, Newmark time integration, or static case. Actually, it doesn't do anything. It's because kx equal f is already the same. So in static case, it doesn't do anything. That's what we were solving at the moment until now. Yeah, these are about the schemes. Then you have something called builder and solvers. I'm just telling you this actually just to know only, because you don't have to deal with it at all unless you are doing something really in-depth study. So the whole purpose of build and solver is to actually take the local kx equal f and assemble it to the global system matrix. I hope that you understand when I say local system matrix and global system matrix. So that's the only purpose of this. There are multiple ways of doing that. I think in IFM or all the other courses, we are doing it by tables, as far as I remember, but that's not its handmade way, but there are multiple other ways depending on the use case. One may be better for other than other. Like the block builder and solver, which we use usually, is not good in context, but in the elimination builder and solver is good in context. But elimination does is basically it removes all the digital boundary conditions because those are anyways predefined and reduce the system matrix size. It's good for context, but not for basic cases. But first one is not good for context, so it has its own merits and demerits. Yeah. So the build and solver is also the responsible since it's removing some DOFs if it is in the elimination case. So it's the one who is responsible to apply Dirichlet boundary conditions. Remember Neumann and Robin boundary conditions coming from the conditions, which I told you, elements and conditions. Like it's just a contribution coming from local matrix contribution, basically coming to the global matrix contribution. So if you are developing, let's say, a wall law for fluids or heat flux law for the convection diffusion, so then you have to develop your own condition, which gives us a local system matrix. Then it is contributed to the global one. So that's how you get that wall law or something to the system matrix for your solution. Dirichlet boundary conditions you don't do specifically. You just pass it to the build and solver, it will automatically do it. Yeah. So it's using equation IDs to construct the global system matrix. After you are getting that, so you now have the global system matrix, then you need somehow to solve it. That's also not an easy task, basically, because those are not so nice matrices you get. Sometimes they are highly ill-conditioned. Sometimes you need special tricks, all those things are there. So whether you use Newton-Raphson, I think everyone knows when I say Newton-Raphson, but do you know Picard? Okay, you know fixed iteration, right? Fixed point iteration. So it's the easiest one to do basically for nonlinear problems, even though the convergence is questionable depending on your starting point and your convergence criteria. So Newton-Raphson uses the first order gradients. Fixed point uses zero order. Basically, it just uses the fx. Picard, you can think of it as in between one. So Newton-Raphson is second order convergence, and the Picard is first order convergence. If you like to know more details, you can ask me because it's a little bit mathematical. So I will skip exact details basically. But in the linear case, if you have a linear system of equations at the end, not a nonlinear one, Picard and Newton will give the same answer. But in the nonlinear case, they differ. Yeah, that's about small indication. So I'm getting another chat. Okay. I'm not sure about that. Haven't watched Star Trek, so no idea. Maybe, yeah. But it's the same spellings? I don't know. I don't know. You are the best judge of that. Yeah. Yeah. Okay. Yeah. So then I told you about the boundary condition. I showed you some processes applying boundary conditions. So the processes are not only used to apply boundary conditions. They have a big scope of applicability in different places. Like you can use processes to maybe update your elements active states. Like in the rotating these two things. So you can use a process to update whether which element gets activated when you rotate like this and all those things. The basic concept of process is actually just to infiltrate your whole solution procedure and put something new. It can be boundary condition also, it's fine. It's just something putting new and changing with the time. Or it can be totally new things like in optimization, putting some new constraints while on the run, saying something like that. So this is just to infiltrate the whole simulation process. We use processors. There's no limitation. There are hook points, basically we call them interfaces, or so that you can infiltrate. So as I told you in the run solution loop, we had all of these are hook points for processes. So every process which we can write in Python or C++, we can write processes in Python or C++. We don't care. It can do something special in the initial solution state or something special in the solve solution step like that. Every point is there's a hook point. So then it gets executed at those points. So that's the purpose of the processors. And there's a whole list of utilities. They don't have an common interface because they are utilities. That's why we are called it utilities, not processors, because they don't have a common interface or API. They have their own methods. These utilities are used within C++ or in Python. Most of them are exposed to Python, not all. And most of them, I would say around 90% are MPI or shared memory, distributed memory compatible by default. One good thing is when you use these utilities, you don't have to say that you are running in shared memory or distributed memory. Automatically detects it and switches the backend. So you don't have to worry if you're working in Python whether, okay, do I need to do something specific for distributed memory? No. That's automatically handled by Kratos backend. But in C++, you might have to deal with it because in C++ you can do, because we give the full access, so you can do crazy stuff there. So you need to be careful. But Python, we kind of expose it like that. I'm not saying 100%, but 99% is enough. Because I cannot guarantee for 100% because I don't think it's hard. It's really hard to know the full Kratos. It's, I think, more than 2.1 million lines of code, the whole Kratos. It's becoming a monster, basically. Yeah. Now, before going to this, let's do the practical session. Okay. Now, we don't need any of this. We will just open a new one. We don't need a MDP and nothing. So I will just open a new folder. And then we will call it, okay, beam example. So what we will try to do now is, I should have changed the order. This example. We will try to solve this example without using any preprocessors, just by only using VS Code. No measures, we will do the manual meshing. Everything by hand. Yeah, this is the example, but I don't know how to keep this. But I think you have the slides, right? Because I get half screen in this screen is not so nice. I think that I will try my best. Okay, let's try half screen. Yeah. We can increase the size in here. Yeah, so I will just create a Python call beam example.py like this. Yeah. Since I am gonna need the hinting because, to be honest, I also don't remember all the methods and I don't want to print dir every now and then. I will switch to my office computer which has the hinting because it's Linux, so it has hinting nicely. For Linux, you can fix the hinting. I will open recent. Okay, I will just use this master. Yeah. We'll just create here. So beam example.py. Half screen, I don't need this anymore. Okay, wait. Yeah, it's good. Yeah, now you have a blank slate, I would say. We can make it larger and then we can close this actually. Yeah. First thing you will do is basically import Kratos Multiphysics as Kratos. That's the first line. So you import the Kratos. Then you need to create this geometry first, basically the mesh, and then the mesh. So I will create a method called def. Okay, first another question. So everyone knows basic Python, right? Yeah, fine. So I will just create a method called create, I don't know, model, which returns a model, Kratos model, basically. So now you see I get the C++ versions because my hinting works because I'm connected to Linux using this SSH here. That's the SSH plugin, so it works nicely. Or in Windows, and another way is actually you can use, I forgot to tell, WSL. In Windows now they allow installing Ubuntu within Windows. Then you can do the same thing. So you don't have to worry about setting it up for Windows. So you're just running Linux on Windows then. It's faster also compared to other methods. Yeah. Let me check. I have it installed, but I didn't configure it. Let me check. Let's go to uninstall. Okay, fine. Oh, it uninstalled it. Oh, sorry. Then you have to check. Maybe, I don't know, 1 GB, maybe, I don't know. Yeah, just check it. It's there in the Windows Store. So it's legitimate. So you can just search it in here, Ubuntu. Yeah, so you have here, take the latest one, not the older ones. So like this. And then just say get install. So you get Linux in Windows. Then you will get everything which Windows user has, Linux user has. That's nice. Yeah, so since I have the computer there, so I don't need the WSL. So yeah, first thing is I will create a model. So Kratos model. This is the first step which we will do in any Kratos problem. Model, as I told you, is the main big container having everything. Then we need to create a model part for the beam. Since we only have one material type, we just can live with one model part. So I will create, it's called, I don't know, I will call it structure to be consistent. Model dot create model part. When you have the hinting, you get some indication about what are the arguments. If you don't have the hinting in Windows, yeah, you don't get this information. So that's why I have to use the Linux one so that I get the hinting. Yeah. So it says here basically two options, string basically and int. We don't care about the int. We just use the string. That means the model part name. So I will call it structure. So for the testing, it's good to that test everything step by step. So I will create a if main method. And then model equals create model. I will just call it. And then let's see what this structure is. We show you every step of the way. Like this. Okay. Okay, for the time being, we don't need this. So we just make it full screen. So you can say now, I think I have it here. Beam. Yeah, it's there. And beam example. So you see, I created structure model part. Okay, this is the print. And then I'm in a different point of the Kratos than what we did in morning, because this is one of my branches of pull request I'm working on. That's why it's a different name, but you will get a different name. So no worries. And in Linux, yeah, it uses my 24 cores, which are limited. Then you have structure, but nothing is inside here. 0, 0, 0. In here, one important step is the buffer size. What does it mean? This is the number of previous time steps it can record. By default, it's always 1. That means there's no previous time step you can record at the nodes. You can change it by saying structure.set buffer size to 3. Now, if you print, you see buffer size is 3. That means you can recall 2 previous timestamps. One is for current always, 2 previous timestamp values, if you like. Because if you think about the time integration schemes, there are some time integration schemes which you need buffer size 3. That means 2 different previous timestamps. It depends on the time integration, basically. Usually, yeah. And you can have tables, the submodel pass are 0, like that. And this is the solution step index, means you are in the current solution step. Yeah. And then you have no geometries, no nodes, properties, conditions, and constraints. So we didn't put anything there. So it's blank model part. Now, what you need to say is, once you set the buffer size, you need to tell Kratos beforehand what kind of storage variables do you need. Why? Because then it can allocate them in a kind of a flat vector so that it will be more efficient. Otherwise, if you say, okay, you run simulation 5 seconds and then you say, okay, now I need, I don't know, temperature. Then he has to rearrange all the nodes, not losing the current values, and then add temperature for every node. Think of it's like a continuous data array. Then you had basically a velocity xy, next velocity xy. Then you need to put everyone's temperature. So then you need to move everything again and again. So it's costly. So to avoid that, Kratos asked everyone to put the historical variables always at first so that they know this is the memory which he will be working on. He or she, I don't know, it. Yeah. How do you do that? So allocation of variables or structure dot add solution step variable. So this is called that. So since we are sorry for the structural static problem, I will just add Kratos displacement. So you see here that's a array 1D variable 3. That means it's a vector with 3 components. This will only come if you have the hinting enabled in Linux. Otherwise, it will not come. That's why I want to show it also, basically. Yeah, but the code will work. Actually, if you follow the code, it will work in Windows, but the hinting will not show up. The same code will work. So you can add displacement. Yeah. If you like, you can add another variable. It's not a must, depending on what you want to see. Kratos reaction. That means we will say in the future to calculate reactions also. If you don't want to calculate reactions, don't add it. That's it. It's up to how you design your problem, what you need from that. If you only want displacement, you can live with displacement for these cases. Yeah. Now we said for each node, we will be looking at these variables. Now we can easily add nodes. Add nodes now. So how do you add nodes? You say structure dot create new node. Yeah, it says we are still working on this. So it says int float. So int is the ID. 1. Okay, another point. Kratos are not having indices, it's ID. So it's always start with 1. If you accidentally use ID 0, it doesn't throw an error, but you end up having like hard to debug errors. It doesn't throw an error, but it will be a silent bug. It will run the simulation, but will produce something different, totally different. Yeah, so be careful. Never use the 0 for IDs in Kratos. That's why it's called ID. If it is an index, it should start with 0. IDs usually start with 1. So now you have to give X, Y, Z coordinates. As I told you, nodes are always 3D. In GID also, it's 3D. If it is 2D, we just put 0 in the Z direction. Now I need again basically this one so that we have the nodal coordinates. I don't want to remember them. Yeah. So now the node 1 is here, 0, 0. So you can create the same nodes. 2 is 3, 0, 3 is 6, 0, 4 is 9, 0. So let's create nodes. Okay. 2, 3, 4. So this is basically 3, 6, 9. Like this. So you created first 4 nodes. Then we just can copy paste this block. I don't know how familiar you are with VS Code shortcuts. I can tell you some tricks to these kind of things. You can just select here this part with mouse 0 to until the end of this one and press Ctrl D. So it gives you multiple cursors. in VS Code. 3, 4. 4 cursors. Then you just say here, basically 1. All 4 lines becomes 1. Like that. Those are shortcuts in VS Code. Yeah. So again, but this one you have to change manually, by the way, the IDs, because you cannot have duplicated IDs. It will throw an error in Kratos. So you need to, this one to be 5, 6, 7, 8. Like this. Again, you need to repeat the same exercise. So this is 9, 10, 11, 12. Again, select 1, 0. You see, automatically VS Code highlights what are the possible control D locations. Press D, so you get the next cursor, next cursor, next cursor. And then say, here, I think it's 2. So now you have created 12 nodes for this problem. So all of them basically, even though it says any, yeah, that's not a problem with Kratos actually. That's a problem with the hinting utility which we uses from Python. It cannot understand some of the C++ stuff. So we have to live with any. In Python, any means it can be anything. That's why it's called any. Usually this one returns a node. When you create a node, it returns a node. But at the moment, the node type, it says any. So it doesn't know the node. It's returning a node. You can help VS Code to understand it's a node. Saying like this. Remember the double dot and saying the type. Now VS Code interprets this as node. Now let's look at the interface for node. So if you say node dot, you have a lot of methods here. So the ones that are interesting is basically you have x, y, z. Those are nodal coordinates. x0, y0, z0. That is the undeformed configuration coordinates. X, y, z are the deformed configuration. For I think if you know the structural mechanics, you have deformed and undeformed configurations. Sometimes they are called reference configuration and current configuration also. It's like just different names. Yeah, so you have this. And then you have basically get solution step value here to get the solution step value. So in here, you need to pass a variable saying, let's say that you want to get displacement of this node, displacement. So this will return, I will just print it. So to show you, print. Let's not print the model part because it will clutter everything. Here, 3. Number of components 3, each component 0, 0, 0. So this will return the displacement of all, or you can say, as I told you, if it has components, displacement x. Then you will say only 0.0, it's a scale. That's how you can get the values. How do you set the values? Let's set it before node.set solution step value. If you want to set only a component, for some reason, you can say 1.5 like this. You can set this node's displacement x component like this. Then you see here, it returns 1.5. You can set it to the previous time step also if you like, put a comma and then say 1. 1 means the previous time step, 2 means the 2 previous time step. Like it goes from 0 is the current, 1 is previous, 2 is previous, like that. The time step access. So now if you print it, you will see that it's still 0. Will print it. Okay, what is? Give me a second. I may be doing it in a different manner. Okay, give me a second. What is the error? Node double 1.51. Okay, double. Sorry, my mistake. So the step should come before. Yeah, now it's 0. But if you want to print the previous time step, just have to say again 1. Get and set same using the same. Yeah. So here it's first prints to 0, then prints the 1.5 because it's set in the previous time step. So this is another important method in nodes. Then, as I told you, there's a set value, which is not historical. It doesn't have any history. It overrides always the current value. In here also, you can say Kratos displacement. And since displacement is a first order tensor, so you need to provide a first order tensor. So in here, how do you say array 3? Then you give values 1, 2, 3, whatever. So displacement has 3 components. You need to give array 3. You need to use Kratos array 3 here. Then if you print it, see, it's the same. So you have get value Kratos dot displacement. Let's not use displacement because it's overwritten here. Let's use basically here velocity, because otherwise it will have mixed results. You see, velocity is 1, 2, 3, but it doesn't have history. So whatever you do in there, you cannot ask for the previous time step. It will be overwritten. Yeah. So that is how you can access the data value containers of the nodes, historical one and non-historical one. And I told you about the flags. How do you access the flags? Node dot each. Then you need to pass a flag. So this can be Kratos active. Those are flags. So it will return true or false. It's false because we haven't set it. If it is not set, by default it's false. So these are the flags. Is for all of these, you never know whether these are already there or not. So all of this has methods. Node has. You can check whether the velocity is there. And then you can check acceleration, which is not there. Like this. So last two, yeah, it says velocity is there, but acceleration is not there. So you can always check whether the variables are also there in Python. This is in the non-historical one. In the historical one, you can also check node dot has solution step value. Then you can ask whether you have Kratos displacement. Yeah, it's true. That's wrong. That's how you can check, because it's important to know how to check and how to get and how to set everything, because otherwise you don't know what you're doing. Yeah. So this is the basic introduction to nodes. So this, so I will just put this also down. This whole block is common to conditions, elements, properties, model parts. All of them has set value, get value, is, and has. Because as I told you, everything has a non-historical container. So all of them can be used to store values. In what manner, it's up to you, basically. For different cases, we use different places to store the values. Yeah. So that's about the nodes. So we don't need these nodes separately. So I will just delete it. Yeah. So we created the nodes now. Yeah. Now we have to create the domain elements. How do you create them? Same way. Before doing that, let's create a submodel part for the domain. Just show you. So I will call it basically solid, which we already had. Solid is equal to structure dot create submodel part. So I will call it solid. So this is how you can create submodel parts. You can create submodel parts nested. It's up to you. Yeah, now we created solid. Now we want to add elements to this solid, which are basically our small displacement elements, which we used in the other example. Let's see how we can do that, whether it works. So adding elements So we can say solid, create new element. Here, also the arguments I can explain. First argument is basically the name, here a string. And the second argument is the ID, because everything in Kratos has an ID. And third one is the list of nodes. The fourth one is the properties, which I told you, which we created dummy properties. So for the time being, let's say that I don't remember the element name. You need to find out the element name from other example actually, because I don't remember it. New window. Desktop. So we had in here somewhere. Here, this one. This is the element name which we need. So this is the element name 2D3N. Oh no, it should be 2D4N. Because we are now dealing with quads, not triangles. Then the ID. Then the list of nodes, which defines this quad. So let's do half screen. So first element is this, which is 1265. 1265. I went in the anti-clockwise order because, as I told you, otherwise the size will be negative, normals will be inverted. So always you have to, in Kratos, define it in the anti-clockwise. For 3D ones, there's a special order you need to also follow for 3D elements. For 2D, it's always anti-clockwise. 1265. So you cannot say 1562. Then you will end up in problems. Then you need to give some properties. So you need to create properties first, then. Yeah. How do you create it? It's simple. Structure.create new properties. You need to give ID only. You create a new properties. Let's see whether this works. You will see not. It will not. It throws an error. Let's see what is that error. First error is, as I told you, how do you know what are the element types which Kratos support? So when you put something, basically stupid name in here, or do a spelling mistake in here, so the Kratos prints available options as an error. At the moment, it has only these elements. None of them has any physics. Why? We only imported Kratos. I told you, the core doesn't have any physics. It's just basic elements for some things in the core. So we need to now import the structural mechanics application. Oh, I have it. Nice. Kratos. Save. Now let's see what happens. Okay, I will just do a spelling mistake in here. Now let's run it again. You see, now you have a lot more elements than core. You have total Lagrangian, solid spring damper, like a lot of more elements, because you loaded the structural mechanics library. So it added these additional elements also to the something we call registry in Kratos. There's a registry which keeps track of what is being added so that they can call from any application and they get it. So you have a lot of elements now. So let's see. Now I will remove the spelling mistake. I think here. Yeah, now let's see whether it works. Still no. Let's see the error. It says node index not found at 1. But we added 1, right? Why does this error still occur? The reasoning is, as I told you, we added 1 at what? At the structure. But we are trying to create an element in the solid which we didn't add any nodes. As I told you, in the submodel part, it's subdomain. If you have an element, then it needs to have corresponding nodes also representing there. So first, what you need to do is basically, you need to add here solid.add nodes. Here, give the list of IDs, because submodel parts doesn't need to create them again. It just needs to say actually, so these nodes are also used in the submodel part. So you just need to give IDs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. Because we need to add everything because this is the domain one, so we will use every node. So this is how you add the nodes. Now it should not give any errors. Let's hope. Yeah, it's run. No errors anymore. Now it created this element. Also, it also returns the element in here, but it's any hinting doesn't understand. So you can identify it as Kratos element. Then you will see the interface. Yeah, it has a lot more other functions because it has this calculate damping matrix, all these methods, which you can use to get the local system matrix out of the element. And then it has, as I told you, get value. Those things are common. They are there. And additionally, you have these additional methods to get mass matrix, damping matrix, left-hand side, all of these things from element. Okay, now let's create all 6 elements. So this second one is basically this, and then its order is 2, 3, 7, 6. Third one is 3, 4, 8, 7. There's no other way to do this. Actually, you need to do it manually because we are doing manual meshing. 5, 6, 10, 9. Then you have fifth one of 6, 7, 11, 10. 6, 7, 11, 10. Then you have sixth one, 7, 8, 12, 11. Yeah, another point is you can use 7, 8, 12, 11 or 8, 12, 11, 7 also. The starting point of the ID doesn't matter. You just don't need to have always started in the left bottom corner. You can start anywhere, but the order should be anti-clockwise. That's the only rule. It doesn't make a difference if you start in here, say that 8, 12, 11, 7 or 7, 8, 12, 11. It's the same. And now we have created, just to make sure everything is right, I will just run it to see no errors. No errors. So we created 6 elements. Now, okay, nice. We have the domain. But how do we apply this distributed load? For that, we need conditions. That's what we had in the Salome one, the load. So let's add the load. Adding loads. So for that, I will create a separate model part for load, just to follow the same convention as what we did in the morning. Kratos, not Kratos, sorry. It should be under structure, create submodel part, load. Here also, first we need to add the nodes. Otherwise, it cannot create the condition. So this will be basically 4, 8, 12. We only need 3 nodes, 4, 8, 12. Because it's only these 2 conditions which we are creating. We don't need the rest of it for this. Then you can say load dot create new condition. Since we don't want to confuse with the boundary condition properties and element properties, so we will create a load condition, the load properties, which is empty in the structure, just not to confuse. Create new properties. 2. Here, because why it is 2? Because we used 1 in here. Otherwise, if you, even though you say create new properties, if you put 1, it will return the existing 1. It will throw a warning, that's it. Then return the existing 1. Now create new condition. Now we need the name. Okay, I will go back to the other one again to get the name. This one. 2D2N, same format, ID, node integer. So this is 48 and load properties like this. So you need two of them. Two, that is 812. Like this. I think that's it, but I need from the PPT, so I will just make it maximum. Yeah. Now we have created the domain here and the load condition in here. But we have not created a possibility to like apply digital boundary condition saying, because these are variables which we said may be used. But all of them are not degrees of freedom of the system. Reaction is not a degrees of freedom. It's just a like final result, basically. But displacement is degree of freedom. So we need to tell it beforehand, before the solving. So what do? We iterate through every node and add this degree of freedom, saying that this will be used as a degree of freedom in the future. How do we do that? First, iterating through the nodes. For node in structure.nodes. That's how you iterate through nodes. If you like, you can print the node. So let's see what it prints. So you see here, node 1, 0, 0, 0, 3, all the locations. And it says nothing about the degrees of freedom because we haven't added any degrees of freedom. Once we add, yeah, in here also node is any. So just to give a Python indication, it's a node. So I just use this line. So I get the Python hinting. It's not required by code, but it's nice that I get the hinting. Node dot add of. That's how we add the degree of freedom. So these degrees of freedom cannot be other than scalars. They can only be scalars because degrees of freedom are always scalars in Kratos. So in this case, you need to add Kratos displacement X separately, Y, just to make sure is it. Even though it's not used, just add it. Because there are some places where if you don't add Z, they throw errors. Because they are meant for being running on 3D, but we use them in 2D. So yeah. So just to be safe, just add Z. Now, if you print the node, you see it says here, it's free. Those degrees of freedom free. It's added as a degree of freedom, but by default, they are free if you don't fix them as a digital boundary condition. That's what it says. Now we added them. Yeah. So we are kind of now at the point where we have everything, the geometry and the mesh is done. One thing basically is, okay, we forgot to add the fixture boundary condition that we need to add. Let's add it here. Adding fixture. Oops. So I will create a fixture equals structure dot create submodel part fixture. And then it's just a nodes only because digital boundary conditions are applied only nodes. You don't need any elements. So I just say add nodes here and pass the IDs. So those IDs will be 1, 5, and 9 in the future to fix them because we need a separate domain or group like what we did in Salome. Left edge, right edge, load. Now we need fixture and then load separately to do different things. So it's 159. 159. Yeah. Let's print the final model part. Print structure now. Let's see what it prints. So you see here, we have a structure model part, which is buffer size 3, even though we don't need buffer size 3 for static cases, but we set it fine. And it has 3 submodel parts. Total number of nodes are 12. It has two properties. One is for elements, one is for conditions. It has 6 elements, 2 conditions. And the first submodel part is fixture. It has 3 nodes only, nothing else. And then you have a load, which has 3 nodes, 2 line conditions for applying the load. And you have the solid, which have 12 nodes and 6 elements, which is the domain nodes. Like that. So I just print it. Now we have created the model. Nice. The next thing is you need to apply the properties for the domain elements. So I will call it apply material properties. So you need to pass a model. Yeah. So how do you apply the material properties? So actually, yeah, it's fine. You don't need to pass the model. You can pass the solid, basically a model part. Tell it will be model part. Yeah. No, actually it should be. Yeah. So you pass structure model part. In here, you first get the properties. Structure dot get properties, the one. Because for elements, we put the ID1 properties. Now, properties. Give me a second. I need to look at the CL and this one. Because I also forgot actually, like, okay. Yeah. Yeah. So you need to first create the constitutive law. Yeah. This is called constitutive law. How do you get this name? It's basically from the other simulation. So if you go to structural mechanics, you have the constitutive law name here in the JSON. So you get that name, and this is how you get the constitutive law. CL, and then you put it to properties. So in here, you see that properties also has any, so you can inform it to the Python, the VS Code, basically saying it's properties. So it knows, and then you get the dot. So if you don't get it. So you can say set value, Kratos constitutive law equals CL. Or you can easily say properties bracket, Kratos constitutive law equals CL. Both the same. Whichever you think is easier. For get value also, you don't need to always use get value. You can use the square bracket. So I will just use that because it's more nice to read. Yeah. Then you need to set properties Kratos.Young's modulus to, I don't know, 206.9 E XGPA 69. Yeah, 9. And then properties Poisson ratio is 0.29. The same values. So if you're not sure what you're doing, it's always good to check. How do you check? You can say in here, after getting the model, you can get the structure. Now you need to apply material properties, model, dot get submodel part. Get model part. So structure dot, so that's it. Yeah, structure. So you apply the properties to structure, and then you can iterate through elements. First, you need to get the structure model part. Okay, I will just put it in the top. It's easier then. Yeah. Then you can print element dot properties Kratos Young's modulus just to see whether it's updated correctly in every element. Because we fixed it in one property only, which we assume it's shared among all the elements. Let's print and see. Let's hope that it runs okay. Okay, I'm not returning here the model. Okay, that's my mistake. I'm just saying it returns a model, but I'm not returning. So you need to return here the model. Okay, it prints here. So it's updated correctly for every element. Even though we fixed it at one property, so it's updated in every element. So nice. So that means our properties are correctly working. So we can just comment out this one. Now we have done the properties. So the next point is basically we need to apply the boundary conditions before solving. That means load and fixing the left edge. So let's say def apply boundary conditions. Okay, for this we need the model because we need to apply it in different model parts. First, let's apply the digital boundary condition. So how do you do that? You need to iterate to the nodes. So node in model on the model parts, submodel part structure, we set it fixture dot nodes. So this is also a shortcut for get model part name. Either you can use this or use this. Both are the same. Like this. Both are the same. But this is more readable, I understand, but other one is shorthand. So we have so used to the shorthand, but I will use this here. Here also the node is basically any, so I need to say for VS Code what is node type of node so that I get the tooltips. Now you say node fix Kratos displacement X. Like that you can fix. Then Y, then Z. That's how you fix or free. But you can free also if you like. The fixed ones you can free. That's the digital boundary condition application. So you can change it between iterations also. It's up to you how you do it. Yeah. Now applying the load. Yeah. So how do we do that? Since we have a distributed load, we need to apply it for the conditions. So we need to iterate through for condition in model dot get. I will just use the big name structure dot load. Now we iterate through conditions. Yeah. Now we need to know the variable name which we need to fix. So since I will just put here condition also as Kratos condition, we need to set the value. The variable name, it depends on the type of solver you use. For the fluid ones, it's different variable names because it's different physics. For structural ones, it's different physics again. For MPM, it's different. So you need to know which variable they are using. So easiest is you look at the example and then see what they are fixing here. So its displacement is fine. It's line load, the variable name. This is the variable name here. That's what they are fixing, line load, to have a load, distributed load. So we use the same variable name. Only thing is, which I'm not sure, is whether it's in the core. No, it's not in the core. It's in the Kratos structural mechanics application. Line load, and it should be Kratos array 3D. Array 3, so values should be how much? Okay, I haven't given. Okay, let's put 10 there in while. 0 minus 10, 0. Like this. So it sets for all we have only two conditions. So both of them -10. It's distributed load. Now we have applied the boundary conditions. Let's see whether what I have done is correct, because I can make mistakes. Apply boundary conditions. So you pass the model. Yeah, no errors, so it's fine. It doesn't do anything yet, but no errors. That's a good sign. Okay, now we have done everything. Boundary conditions, material properties, and basically the geometry stuff. Next is, how do we do the solving? That's going to be a little bit cryptic also, but I will try my best to be explanatory. Yeah. So let's create a method called def solve. Model. Model. So in a Kratos context, I told you strategy is the one which is solving everything. And there are a lot of strategies. Let's use one of the strategies in Kratos. Let's do, I would say, the reverse engineering way, not the top down, but the bottom up. So we will find out what we need on the way. So you need a solving strategy that we know. Strategy equals Kratos dot, I don't know, residual base Newton Raphson, some residual Newton. Yeah. So we use Newton Raphson. That's the solver, basically. Yeah, now this has a lot of arguments. So it needs a model part, sure, that explains the domain or multiple domains. And it needs a time integration scheme, because this Newton Raphson is not only for static ones, it works with transient ones also. It may need a linear solver, or it may need a built-in solver. It's up to us to decide. Then all the other arguments are basically, one of them is eco-level, other one is mesh moving, compute reactions, mesh moving, and other one I also need to refer basically. Yeah, what are these arguments? Those you can find actually in Kratos. If you need to find them, basically, you need to you don't need to compile Kratos. You can just go to Kratos. Okay, I have Kratos here, right? Yeah. Go to the structural mechanics solver. So you go to the applications in Kratos, which are as I told you. So in Kratos, we have a core. This is the core. And then you have the applications. Applications are maybe utility or non-utility. So in the applications, you have here all of the utility and non-utility, Chimera, maybe fluid dynamics. So all the applications are there. So you can go to the application which you are interested in. In our case, structural mechanics. And under that, you have some folder structure called, this type of folder structure is there in every application. It says custom conditions means boundary conditions, Neumann or Robin. Then you have custom constitutive, that means constitutive laws specific for that application for structural mechanics, because fluid has its own constitutive laws. Then you have the custom constraints, that's for constraint problems. Then you have custom elements, those are small displacement elements or beam elements or whatever. Then IO is just to output and input. And these are the custom processes, as I told you, to infiltrate your simulation process. There are a lot of processes like, Prism neighbors, I don't know, different applications, different reasons for that. Then this is for custom response functions, it's just for sensitivity analysis. We will not look at it today. And then you have custom strategies, which has convergence criterions. And then you have schemes. So you see here static, Bossack, different schemes. These are time integration schemes. And then strategies like icon solver strategy, pre-buckling, like different strategies apart from the Newton Raphson. Newton Raphson is from the core. These are some new strategies to solve different things. And utilities are there. As I told you, every application can have its own utilities. So custom, this is the folder structure in every application here. Then you have the Python scripts, which has all the Python scripts. The first place which you can look at is actually, if you have a problem, is to identify where it is coming from the Python, because that's where the execution first starts. So for structural mechanics, so this is the structural mechanics analysis which you imported in the morning unknowingly. So this is the file. So it's derived from the analysis stage, as I told you. So it has some specific tasks, but it's not a long file. So it's some small task. So every analysis needs a solver. The solver, we call it a Python solver, which is here, structural mechanics solver. So it has these methods to be overridden by different purpose. Let's say that if you're looking for static structural mechanics solver, so you need to look for here structural mechanics static solver. That's what we are now checking. So here, so you will see it's simple class. It's only create a scheme, which is a structural mechanics static scheme, because it's a static problem solver, Python solver. In the structural mechanics solver, if you go to here, the solution strategy method, yeah, it says here, this is where we create Newton Raphson. So this is how you can create Newton Raphson. Basically, these are the additional arguments which are not self-explanatory. First one is the max iterations. How many max iterations in Newton Raphson in each time step, and whether to compute reactions. This is to do if you have remeshing enabled, like means if every time step you do a remesh. So then you need to reform all the dots again, because you might have new nodes or you might have removed the nodes. And the move mesh means whether to move the mesh after the solution, because in structural problems we need to move. Fluid problems we don't move. So basically that. So that's how you can find out. Basically, just following the Python route. It's not easy, but unfortunately, that's the way. Yeah. So I will just copy paste this from this block and put it to our one. Okay, where is our one? Yeah. So I will just put it here as it is. Yeah, like this. So this is Kratos. Now we know that we need a computing model part, but that we know it's model structure. So we can replace it. So we need a scheme. And we know that there's a static scheme from the Kratos. So you can go to structural mechanics static solver. This is a static scheme. The scheme should be before. It's Kratos essay for me because I imported it as that. Then it asks for some parameters, but I think we can leave it blank. So this is the blank parameters. So scheme is done, so we can just put it there. And you need a convergence criterion. So convergence criterion, you can use it from the core actually. You don't need the structural mechanics one. I think residual criterion should be there, residual criteria. So it checks whether the residual is reached some value. Yeah, so there are two values. First float is relative tolerance. Second float is absolute tolerance. So by memory, I'm putting it. I understand like this. So it checks whether your residual has reached 1e minus 6 relative to the initial residual, which you had in the time iteration, or the absolute tolerance is basically 1e minus 9. Then it says it's converged. So that's the convergence criteria. It says it needs a built-in solver, so we can create the basic built-in solver. This doesn't change actually between lot of different physics. Not all, but most of the physics it's the same. Built-in solver. You can use the Kratos residual lock. This one. It needs a linear solver. So that's how I said we are doing bottom up, figuring out what we need. Because Otherwise, it's a little bit hard unless you need to know endpoint where you execute, and then you can do reverse engineer. Even otherwise, I don't also remember all of these, to be honest. Yeah. So you need linear solver now, or we need to create a linear solver. So how do you create a linear solver? Kratos. Create. Let's see whether it works. I'm also not sure. Because maybe it's because I forgot. So I will tell you if it works, how this is working. GCA, let's put that. Let's comment out these things and then see whether the linear solver works. Yeah. Okay, it's a object. It works. It gets so okay. How do I get these settings? So in the solver type, usually you will see it in the code structural mechanics solver. In every solver, there are default settings at the top. Here, these are the default settings. In every Python file, you will find this kind of default parameters. You can just search for it in here. So every Python file, even in C++ processes, you will find default settings. That's how we navigate. I will tell the shortcut also a little bit later. Yeah. So you see here, so you go it here, here, here. Okay, there's no linear solver here. Oh, seriously. Okay. I was expecting it, but okay. Yeah. So these are the default settings, which if you don't specify any of these, they will use these defaults. That's the meaning of default settings in Kratos. That's why, so you see, for each solver, there's a lot of settings, but GRE sets maybe half of it. Rest is defaults. So that's why GRE doesn't support the full capabilities of Kratos. So linear solvers are not there. Let me try to find out whether any of them has it. Please, this one has it. Nope, it doesn't have it also. Just to show you, because explicit dynamic anyways doesn't have it. This one, nope. None of the solvers has. Okay. Yeah, then you need to trust me basically. Maybe fluid ones has it. Yeah, fluid ones has it. Not in structures. I'm for sure Rans has it. Not even my solvers, I did put it. Okay. Let me try to find something. Fluid dynamics, Python. Yeah. So every solver usually have this block, but it's by default nested. So that's why you don't see it others. So they get it from the default linear solvers. So usually you have it. So this is the linear solver settings. Usually you have a solver type. In structural mechanics, we use automatic by default. That's why this line is not there. But in fluids, there's no automatic. Because fluid matrices are super crazy. So you cannot judge it. So in that case, we ask the user. So MGCL is there in Kratos code. That's why I used it. So this is how I know. Basically, you can also, basically, you need to like go through the structural mechanics solver to understand it. It's not so easy, but that's how it is. So we created the MGCL solver now. It's an iterative solver, not direct solver. Now we can do this and then pass this linear solver here. Let's run it to see whether no errors. No errors, nice. Then we can do this and this. Finally, we can enable all of this. So we will say here max iterations, I don't know, 100. I think it should solve in one iteration anyways. Max X iterations. Then compute reactions. Okay, let's take true. Compute reactions. Reformed of, since we are not doing remeshing. False. Reform dots. Okay, move mesh. It's up to you. I will say false. Yeah. Like this. So strategy is also done. Now let's say whether we can solve. It's a miracle if it runs and works in the first place, because I did it on the fly basically, so I might have missed some things. Let's check our luck. Yeah, as expected. Yeah, this we forgot. Since we want to calculate reactions, we need to link reaction variables basically correctly with the displacements. For the time being, I will comment it out and then make the reactions false to make it simpler. It works. That's good. At least only one error. So as you saw, it's converging in one iteration because it's a linear problem. It doesn't matter you use Newton-Raphson or Picard because linear problem solves in one iteration in Newton-Raphson. Yeah. So it converged and it reaches 1e minus 30. But that's a problem. We don't have any output. Nothing actually. So how do you put the output? Because it just runs it and solves it. That's it, you know. So how do you get the output? You can use Kratos output mechanisms. I will not show you the GID one because I'm not familiar with it when I code, but I will show you the parameter one, which is I'm familiar with. So you can create it's called VTU output. You can create Kratos VTU output. Actually, not that one. Let me move to Windows now, because I installed it in Windows correctly, not in my own computer. So I will move this whole file to the Windows. Not this one. Yeah, this one. So beam example, I will just copy paste in here. So let's see whether this runs now. CD beam example, Python, beam. Oh, it runs. Okay, still it works in Windows. Yeah. Now I'm also flying blind like you without Python hinting. Let's see how far I can go. VTU output is the one. It's in Kratos, future, VTU output. There's this new concept called Kratos future, which we put new features first now there, not to disturb the existing features, because there's a VTU output in normal Kratos, which we want to kind of get rid of because of this new VTU output has a lot more capabilities. So that's why we put it future, and then there's a transition period, usually 6 months. Then after we remove the old ones and put the new ones in the old ones place. That's how the Kratos works, because otherwise we are killing a lot of other people if we directly introduce new changes to the system. So in here, VTU output, you need to put a model part. So I will just put structure. And I will say VTU output dot add variable. Let's fly blind and see whether what errors we get. Yeah, now you can say you need to visualize with displacement. Displacement, yeah. Since it's add variable, it does not know from where, because as I told you, elements conditions also can have displacement, because it's just a data value container and this is just a variable. So you need to tell from where to output the displacement. So I need to tell Kratos, I think it's globals, data location. I'm just putting it by memory. Node historical, most probably. Let's see. I'm also not 100% sure. Oh yeah, it worked. Okay, my memory is good. Yeah, it worked. No errors. So my memory is good. Yeah, but so this is just adding the variable, not telling it to still output. Now what you can do is you can say v2 output dot print output and just give a name. Let's say step or no, let's say beam like this. Then, so if you look at this folder, so nothing is there in this folder. If you run it, you get this pvd file, which called paraview data file. You can read it, it's XML file. And then you have all the information in here, basically for different types of variables, conditions, elements. So displacement is there, it's binary, so you cannot read it. Sure, it's compressed binary basically. So, but displacement is there. So now you can visualize them. Let's delete. Let's go to beam. Open the pvd file. Applied. Yeah, this is the domain. Let's see displacement. This is displacement. That's good. So this is how you can visualize. Also an output, basically. Fully in a scripting manner, without using JSON, nothing, just Python. You can use Kratos fully with Python. You don't need JSON even not even a mesh file. Then you need to generate your own mesh. Sometimes we do that for parametric studies also. It's easier. That's why Salome becomes more handy, because Salome can create a Python file to generate a mesh. So you just call that in here rather than you're creating it with different parameters. So it generates the mesh and then we read it from Kratos. Everything happens in memory. Super nice, super fast. Okay, now we have done one example. Now let's look at a little bit of advanced but flexible stuff. For that, I would like to introduce the next topic. I should have put it down. This is super new to Kratos. I would say we did it maybe 3 months ago. We had something similar before that, similar to this before that, like we did 2 years ago. And then we kind of, as you know, Kratos is always changing. So we thought of a better design. So we changed it, obviously, with a lot of output from others. So now we call it tensor adapters. So first thing is, why tensor adapters? As I explained, Kratos has multiple data containers. It can be nodal, it can be elemental, it can be in the condition, it can be in the model part. There are a lot of places. Some I didn't even mention, like degrees of freedom also is a data value container. So there are a lot of others. Master, the constraint, like master slave constraint, is also data value container. So it has a data value container. So there are a lot of things which I didn't mention because I didn't want to go into exact details of everything. Yeah. So, and they have multiple data types. Double 3D vectors, tensors, dynamic vectors, dynamic matrices. So a lot of data types for each data container. So the next point is we were thinking of we need efficient prototyping methods. Why? Whenever we want to do something, we don't want to always go to C++ and then like do everything in C++, which takes a little bit of more time because we need to understand a lot of things like, I don't know whether, templating and all those things. So we want to have fast prototyping. And the most important point is coupling with external libraries. That was a driving force for this, basically. Because this makes our life easy to couple with any external library if it has a C interface or NumPy interface. We only need those two. Yeah. So that's the purpose of tensors. What is a tensor adapter? You can think of it as just a vector of values. So as told you, let's assume that you have two nodes with velocity x and y. So you can put them as node 1 velocity x, node 1 velocity y, node 2 velocity x, node 2 velocity y, just in a single vector. Tensor adapters, the concept is that in the backend, actually it is that to be faster, because always these flat vectors are super fast in computations. That's what we also always go for efficiency. We need to be like that. Additionally, it can have information about where this data comes from, whether it comes from node displacement, node velocity, or element velocity, or degree of freedom, something. So it has this additional information. It depends on how you create a tensor adapter. The location information is also there, and a flat vector of values is there. It doesn't matter whether it's you are storing array 3D or you are storing a tensor, it doesn't matter. It's always a flat vector at the end. We keep the information about the shape to recover the tensor information. So that's how we do it, tensor adapter. So basically, it's a collection of a flat vector and a shape and a location information where it comes from. Yeah. Since we keep this information, we have two methods, basically. It's called collect data and store data, so that if someone from NumPy or C++ gives some values to these tensor adapters, it can store correctly in the displacements of the model part. Whatever values come from NumPy, you can store it in displacements directly, or accelerations, whatever the variable you want. You can do vice versa also. You can convert the displacements from Kratos to NumPy arrays, and then do some modifications in NumPy, maybe solve the system in NumPy, we don't care, and then pass it to model part in Kratos again, back and forth. One of the biggest use cases of this is actually in optimization, because optimization is fully built on this concept, the optimization application in Kratos. Yeah. So how do they work? As I told, so you can read nodal values and then fill the flat vector as long as with the data location. And the shape of the resulting tensor adapter is always n. N is number of nodes and the shape of the variable. So if it is the velocity, then n by 3, because it has 3 components, and the first dimension is always number of entities. It can be number of nodes, elements, conditions. The next dimensions are for what is a variable type, because this can store any number of dimensions, like in NumPy. NumPy doesn't care because you can have shape with indices 10 also. 10th order tensor basically, also in NumPy. So read, you can read. And writing also possible from tensor adapter to the nodes. So it uses the shape of the tensor adapter to cross-check whether you are writing to the correct variable or all those things are done. Yeah. Then tensor adapters are heavily used to back and forth get information from Kratos to Kratos also, because it's super fast, because we use shared memory parallelism in there, and it's a flat vector, so it's fast. And then we use it to communicate with NumPy, SciPy. That's how in the optimization application, we can use basically SciPy optimization algorithms, or we have coupled with Pyrol, because any library which has an interface to Python, we can couple using tensor adapters. That's how we do this multiphysics, so that we don't do everything by ourselves. We use the advantage, okay, others has done, so why not use that? Because we know that we cannot do everything by ourselves. It's not possible in current context. And if someone doesn't have Python interfacing, at least if they have a C++ or C interfacing, I don't know whether you know the difference between C++ and C interfacing. C interfacing means basically you only have pointers, the most generic interface. Still, tensor adapters can be used there to transfer back and forth information. And there are other possibilities also like that. But so then there's something on top of that, something called a combined tensor adapter. Since Kratos multiphysics is basically different physics and different domains, sometimes you have 3 elements, and then this is element type 1, not elements 1. So this is element type 1, element type 2. This one can be maybe convection diffusion. This one can be fluid. This one can be structural. I don't care. And then they can have their own tensor adapters for the whole model part. Then you can have one combined tensor adapter combining these 3. Then the combined tensor adapter is again a flat vector, remember. So each one of them also different separate flat vectors representing their own data. Combined one creates another flat vector representing the whole data set, but it knows how to write back and forth to each one separately. So that cumbersome task of mapping the indices to correct places is done automatically nicely. So you don't have to worry about it. The combined one is used again, specifically in optimization to do, let's say that you want to optimize for shape plus thickness plus Poisson ratio. So these are three variables. So you use combined, each tensor adapter will have one first one is shape, second one is thickness, third one is Poisson ratio, like that. You can combine anyhow. That's why the optimization applications uses heavily all of these adapters. Yeah. Then you can again communicate for sure. It's the same for the NumPy and SciPy. Yeah. So benefits is, as I showed, efficient implementations are allowed. Yeah, quick and convenient prototyping in shared memory. Yeah. So we did that. Now let's see how we can use these tensor adapters. Where is that now? This, oh, this, not this one. This one, yeah. Yeah, again, I'm going by memory because I'm now in Windows. So you can create tensor adapters. Let's say that you want to read the displacement to tensor adapter. I will just say this TA. You can create them. Kratos, it's called tensor adapters. Adapters, I think. Historical variable tensor adapter. If you have the hinting, it will nicely show, but I will just use it like that. Then you need to say from where to read, which node to read, because you can have multiple model parts or submodel parts. So you need to say here model structure dot nodes. And then the variable. I will just say Kratos displacement. Yeah, this is how you create a one, but still you haven't read, you just created one. How do you read? You say disk.ta collect data. So it collects from the model part and then to the tensor adapter, to flat vector. If you want to visualize, you can just say disk.ta.data. Okay, I just don't need this for the time being. Let's see whether it runs. Yeah, you see here, it prints. We had 12, so 1, 2, 3, 4, 5, 6, 12 lines, and each one's displacement as an NumPy array. This is an NumPy array. So whenever you say here dot data, it is an NumPy array. And this one doesn't have a cost if you do it wisely, because NumPy allows sharing the backend memories of other softwares. So we don't do a copy in here. We just share the memory between NumPy and Kratos. So no copying involved to be efficient. Again, the efficiency comes into play. Otherwise, if you create a new NumPy array, so you need to always copy, reserve memory, and all those things, we avoid everything. It's done automatically. Yeah. So then what you like, if you like, you can do multiplication of 2 because NumPy allows it, because data isn't now tensor ta.data is a NumPy array. You can do here. So we will see here it prints multiplied by 2, whatever this thing is. And you can assign it if you like. This ta.data equals multiplied by 2. So you can change internal data structure of Kratos in Python easily, even for millions of nodes. No problem. If you can still do it with for loop in Python also, but it will be immensely costly. This allows fast prototyping. Now you set it. Then what you can do is basically, you can say disk.ta store data to write back that the modified displacements to the Kratos. Then one other thing is, let's say that you're debugging. Then you need to visualize intermediate values. You don't want to hack C++ code, and you want to do it in Python. What you can do is you can do collect data here. And then, so we will create this guy a little bit top. Let's move the print output down. So printing happens at the end. So what you can do is here, you can say VTU output dot add tensor adapter. You can give any string name. I don't know. I will say check one value and then pass the diff TA. So you can visualize intermediate values for debugging purposes. I will not do store data so that you can see it's multiplied by 2 basically. Now you run it. Now if you, again, you need to reload basically in PVD. So you see here, check one value is there, which is set to output. Now if you go here, so you have check one value, which 3.6. So this should be, yeah, 1.8. So it's double. You can use any NumPy function and then update anyhow you want and then pass it to TensorRaptor. TensorRaptor is kind of an intermediary between Kratos and NumPy or Kratos and C interfaces, basically. So to have efficient data exchange. That's the purpose of TensorRaptors. There's some other purpose also, but the main purpose is that. So you have different types of TensorRaptors. So historical variable is there, and then normal variable is there for elements conditions because it doesn't have historical ones. So that is there. And then let's say that you want to read node position TensorRaptor. Let's say that you won't read the nodal positions. So node position. I'm not sure about the name. Let's see. Okay, I can check it in my Linux version. Kratos, TensorRaptors, node position TensorRaptor. Okay. Yeah, so that's how it is called. Yeah, node position. It's correct. Okay, nodes. And then now it's not this because node positions doesn't need a variable. So you need to say Kratos configuration, whether it's initial or current nodal positions. Then you need to always say collect. Now it's not this, actually it's X. You don't need to modify, so you can say position. Now if you reload, so you need to delete because the data has changed. Now you have position. So you just visualize the position, basically. So you can modify the position also. Let's say that you want to move these nodes. That's the nice thing I can show. So I want to move, let's say X TA dot data. I want to move which node? It's 12th node. Let's say 12th node. X, Y coordinate. Plus equals 2 by 2 meters, right? So you do this like this, and then you say xta dot store data. You don't need to actually, you will see the modification nicely. So you can just print. Yeah, you need to edit. Oh, no, you don't need to edit. Yeah, you just print it before and after with here beam 1. Beautiful name. Let's see whether it runs. It's 11 because 12 is the ID, index is 11. Yeah. Yeah, it works. So now let's load both of them. What happened to beam 1? Okay, where is my beam 1? Prints beam, but not beam 1. Yeah, okay, in that case, I have a small trick so that we can set actually some variable called model structure. This is just to set the step. So because you can think of them as 2 steps for outputting. Step 1, then print in here step 2. So it should be the beam. Now it should have 2. Hopefully, let's see. Yeah, it has 2 now. So Yeah, it has to be fine. Yes. So if you look at now, it's beam PVD. Yeah, you see, it's moved. We just did it in Python. We didn't change anything in the nodes, so you can do like this, change a lot of stuff in Kratos using tensor adapters. And it is nice thing is it's coupled with Python. Yeah. So that's it with the in like the from scratch part of the Kratos. Any questions or anything you would like to know additionally? Okay. If you don't have any questions, then the next 2 points are basically playing around with some advanced use cases of Kratos, but not building them from scratch because it will take a long time to build from scratch. So let's look at the first co-simulation example. Yeah, first go to model. So you have optimization and co-simulation example. So you can download both of them as zip file. So I have downloaded them already just to explain how they work. Okay, we don't need this anymore. Don't save. Okay, we can have this. I can close the other one also. Yep. The EM example is done. So I already have them. So let's look at the co-simulation. So this problem is basically taken from the Kratos examples repository. You can also again look at the Kratos examples repository. Co-simulation. I think in yep. Okay, not in here. Nope. Yeah, cylinder cooling. This is the example. So you have explanation. It's called cylinder cooling. So this is the example. Basically, it's a conjugate heat transfer problem. They have explained the problem, and this is what we are doing. So there's a structure, fluid, and there's a heat transfer. That's what this example is about. Yeah. And this is not so expensive. That's what I chose it, but it's still a little bit expensive because fluid is involved. Yeah. And in here, we don't do any mesh motion because no structural deformation happens, only thermal. Yeah. So if you look at the example now, let's go through the files. For each physics, we have separate project parameters. That's what I told you. The minimum is 2. Now it becomes a bit complicated. For thermal, you have separate project parameters. For solids, you have separate project parameters. And you have here convection diffusion materials, buoyancy materials. That's it. Yeah. And you have 2 MDPs for fluid and solid. So now the problem becomes a little bit complicated. So you have fluid and solid. Let's look at basically solid one because that's the easy one to look at. Yeah. So you have the same setup. So it's transient. Now we are in the transient regime and it's non-linear. So you have this and then you are reading this MDPA and this is the structural material properties. So if you look at that, so this one, so you see here conductivity and specific heat is there. Basically, and the density. No constitutive law because we are not solving for deformations. Yeah. Apart from that, yeah, nothing else. So this is the temperature boundary conditions. So you apply temperature, constraint false. That's the initial temperature because remember, this is a transient problem. So it's an initial value problem. That means your initial conditions plays a huge role. So you need to have correct initial conditions also. Unless you are looking at the statistical values. That's also a little bit problem actually. So there are some cases where your statistical average sometimes has problems. Yeah. Then you have here, this is the solid thermal interface, which does basically all these additional convection stuff. And this is the output. So that's why. So solid one is super easy to see. That's always the case. Structural ones are a little bit fairly simpler than the fluid ones. So now let's look at the fluid one. It's called thermal here. So we don't look at the output or restart, we don't care. Yeah. The solid type is not thermally coupled. So it has separately fluid and thermal settings. Because as I told you, now you have the same domain with two different physics, fluid physics and thermal physics, which is the energy equation. Like that. Or there are other ways also coupled, like using the buoyancy. What's the name? Using the change in the gravity, basically you can introduce the thermal effect also to the problem, but I forgot the name for that now. Yeah, I will remember it later. Yeah. So let's look at, I'm not going into details of these settings, but you can play around. That's the purpose of explaining me this. So you have here the solid type monolithic. So these are the material parameters. So you see here basically buoyancy material. So you have dynamic viscosity, conductivity, specific heat, which is required for the fluid problem. Yep. And then you have the thermal solver, again, the same material properties. Yeah. And then you apply now boundary conditions here. Velocity at the inlet is 1.0, inverts normal for the fluid problem. And the pressure at the right wall is 0, the far field pressure. And you have applied no slip in the thing on the surface of this fluid one. And slip on the top and bottom as far as I've seen in the result. Yeah, slip on the top and bottom. Yeah. And it also has a thermal phase process, remember. So it also had it. That's how they communicate with each other, like how to transfer values. But yeah. Yeah, so then you have some pressure values. So velocity fixing here at the left wall, you fix the velocity is true. That's what digital boundary condition. So velocity is a digital boundary condition for the fluid problem because we are using Eulerian framework in the fluid solver. And then you have this Bossinus force, basically. So that's the thermal fluid problem description. Now, how do we combine? Using the COSIM JSON. There's another JSON file which combines these two JSON files. That's why it's nested JSON now. It becomes complicated little by little. I will explain because this is where you can play around. I'm not expecting you to play around with the separate solver, so you can still play around, but this is interesting to play around. I'm not sure how well-versed you are with the co-simulation, but in the co-simulation world, you need to couple these two solvers, right? You have the thermal solver, then you have the solid solver. So somehow you have to couple and then converge. How do you couple? Depends on what type of problem you solve and what parameters do you use. So Gauss-Seidel strong means you solve the thermal one, and then you pass some information to the solid one, and then you solve the solid one, and you pass back some information to the thermal one until this interface is converged, it runs. That's why it's called strong. If it is not converged, it doesn't go to the next time step. It will iterate through until the maximum iteration, and then it will throw an warning saying it didn't converge. Because both the solvers needs to, like, passing value should be converging. It can be in the fluid structure interaction. Example is your solid solver will solve for displacement. Then you pass this displacement to the fluid solver because it moves the fluid solver. Because of the movement, fluid solver will create new forces. The forces are passed back to the solid solver. Because solid needs the forces, fluid needs the mesh. So that's one way of looking at it. And then these two needs to be balanced off. That means passing forces cannot change And the displacement, if they don't change after iterations, that makes it kind of like convergence. That's the Gauss-Seidel strong. In the Gauss-Seidel weak, or Gauss-Seidel weak, I can't remember the name, but the weak, other one is called weak coupling. This is called strong coupling. So other one is called weak coupling. In the weak coupling, we solve the fluid once, pass the forces, solve the structure. We don't check the convergence. We go for the type step. There are use cases for both. There are merits and demerits for both. Yeah. Here, so these are the data transfer operators. So how to map? So that was the question for you. Basically, you asked whether you can have different measures. This allows it. So now you use the nearest neighbor mapping. Then you can have an interface between in here the thermal and the fluid and the solid, which is non-matching grid. Then the nearest neighbor mapping will come. Mapper will map back and forth the values correctly. So you don't have to take care of it. You just have to say it. That's the nice thing about this co-simulation workflow. You just separately configure your different physics, and then you separately configure co-sim, which combines them, so that you can separately run the physics separately also if you are given the correct conditions from the other physics like that. So it's modular. That's how it is made. And this is a number of coupling iterations, and convergence accelerators are to make the convergence faster. In here, we don't need them, but we can use them if you like. Then the coupling operations. So this is basically how you distribute the values. So you will see these names a little bit later, then you will understand. And the convergence criteria is basically relative norm previous residual. So they just check residuals basically. Now the coupling. This is a sequence. So it's a list. You can couple 3 solvers also in Kratos. We have some examples for that also. Coupling 3 different things in a list. So in the coupling sequence, we first do the solid. For the solid, the input data list is basically, it says reaction. Where does this come from? If you go to different solvers, you have first solver fluid and first solver solid, second solver solid. So in the coupling sequence, we say the first one is solid. That's the solver solid. And it says basically, what is it? Data reaction from solver fluid. So now we have to go to the fluid and data reaction. So that means reaction flux variable in the fluid. That's what it's reading. That's how you should understand. So it's a little bit mapping basically inside head. So when in here, when it says it's reading reaction from solver fluid, that means it's reading basically reaction flux from this model part. That's what it says. And it says it's putting it data transfer operator as a mapper, so which we said the nearest neighbor mapper. So if it is a mapping grid, matching grid, so it will be faster. Then swap sign to means to actually swap the sign negative to positive, positive to negative. Yeah. So it says basically a mapper to data transfer operator swap sign. Yeah, that's what it says. So the reaction to this solver, that means this is to this solver, is coming from the fluid reaction. So let's take the solid solver's reaction. So that means reaction flux to this model part is read from the fluid's this model part's reaction flux, but with a negative sign. That's what it says, basically. So you need to kind of juggle your head basically to understand. So this is the input data. So this is the where you store in the solid. So that's the reaction variable of the solid. You read from fluid reaction. So you read from fluid reaction, so which is this one, this model parts reaction flux, and store it to this model parts reaction with the swap sign. That's what it says in the coupling. And then it has an output data list. So data temp, you need to check from now. This data is always belongs to this solver, solid. So you need to check solid's temp. Yeah, temp is the temperature of this model part. So you output data temp to solver fluid, the temp. So fluid's temperature is basically in this model part temperature. Again, you should use the same mapper, Nearest neighbor mapper. So you get basically from the fluid the reaction flux, and you calculate the temperatures on the solid and output the structure's surface temperatures to the fluid. That's how this coupling is happening in the sequence. For fluid, you see, you don't have any input output because you already set in the structure the fluid's temperature. The fluid's already set. You don't need to set it again. You can put it as an input data list for fluid. It's your decision. Yeah, it's the same outcome basically at the end. It does, whether solid does it or fluid does it, it doesn't matter. Now then it solves the fluid and continues until the convergence, basically. Yeah, this is the cosim. So let's see whether it runs. It won't, I think, in your version. So because, let me deactivate this. Does it work like this? Okay. Oh, it worked. Nice. So then I will just, I don't know, what is this? Yeah, so I will activate the one which I have. So where is that? See. Do you know how to remove this sticky scroll? No. Yeah, software, Python, Kratos onboarding, scripts. Okay. CD scripts. Yeah. Okay, so then you need to go to co-simulation. Yeah, so you need to run the Python main script. Basically, it's the same. Let's hope it will not run. Sure. I haven't loaded. Why it is not? Let me just don't use release. Use the other one. Let me say, where is that? It's the Python environments. Now it's onboarding. Nice. So let's go to again CD up here. CD scripts, CD pro simulation, Python main part. It will not run. It says you don't have the co-simulation application. You need to have that to run this. So you can easily do it. Python -m pip install Kratos simulation application. Yeah. Now let's see whether what else does it need. All right. So it says it needs the, I think, fluid dynamics application also because we are using the fluid dynamics. Yeah, it doesn't have the convection diffusion application, so we need to have that. And we need the fluid dynamics also because we are solving fluid dynamics. Yeah. It uses a mapper. So as I told you, the mapper is a separate application, so it's called mapping application. Yeah, it runs now. So this is how it runs. Yeah, so we can visualize basically. So we can kill this and go there. See users reset sync and share. can open both. Then you can visualize temperature. Yeah. It's still running. So this is how the temperature looks like. For the solid also, you can put the temperature. So that it's continuous. It's a cooling one, so it's reducing the temperature. And this is how it looks like. It's cooling basically. So this is the simulation. Yeah. So this is the basic example of co-simulation. So you can play around with it. And if you have any questions, we are also here. So it's finished running. It's fast for a fluid problem, basically. Yeah. So you see here as the log file. So we are checking velocity convergence. So you can see all of these things. Pressure convergence and Gauss-Seidel convergence. That means the coupling convergence and everything. Yeah. Okay. So with that, if you don't have any questions, I can go ahead with the next example, if you suggest. Or do you want to try out in this example, or do you want to try it by yourself? Yeah. Yeah. Okay, then we can go for the next example to explain how the optimization works. Yeah. So let's open the optimization. You can download that also in the optimization one. So in here also, you see different things. Optimization also, this is a topology optimization problem. It's one of the benchmark cases of this bridge example. So you have a primal problem, which you need to be optimized. So which is explained by project parameters and structural materials. So this is structural optimization. So we have basic structural problem here. So which defines the bounds of the normal Solver settings, which you already saw. Since this is static problem, so it's fine. Transient optimization is also there in Kratos. Yeah, it's a bit complicated than this one, so I didn't put it here. The transient problem optimization. So you have the boundary conditions, basically. And then you have the point loads, that's it. Simple structure. Just displacement. So this is basically the problem where you have a beam and then it's basically supported by these two corners and then point load in the middle. And then you want to topology optimize it, basically, to see this truss structure, basically. So that's this problem. So this displacement fixtures are at the two ends. And the point load is at the middle. Now this is roller support. Sorry, the right-hand side is roller support. Sorry. Left is fixed, right-hand side is roller supported. And point load is at the middle. Yeah. Okay. Then you have the structural materials. In here. Additional final is basically the optimization parameters, which defines the optimization problem. So let's look at that because that's the interesting part here. It is a little bit different from other things. So you have basically these blocks. Yeah, problem data as it is in the normal Kratos, you have it. We don't care about the name. You can put the problem name. We don't care because it's not even read by Kratos. And then you can have OpenMP and MPI. But MPI is still experimental for optimization. We are working on it. OpenMP is there working. Then model parts. You need to tell where to read the model part. Now, the thing is, structural solver doesn't read the model part because the optimizer needs to update the model part also, right? Let's say that, assume the shape optimization. So then optimizer needs to shape the nodes, right? When you do get up like better design, that means optimizer needs to have control over the model part. Because of that, we read the model part in the optimization settings, not in project parameters. So in here, we have basically use input model part. We don't read it there. So we read the structure, the model part name, and the file is top opt. So it's the MDPA. We can use med application also here. It doesn't matter where it comes from. It just needs to be a geometry file represented. Yeah. Then what are the analyses? Those are the analyses, what we call the primal analyses, which you need to calculate the sensitivities. In this case, it's only one because we support multiple analyses. For multiple load cases, maybe multiple responses, we support list of analyses. Like, let's say that you want to do example with 2 load cases, then you will have 2 analyses here. And then optimize for topology for the 2 load cases. If you have more interest, you can attend the optimization lectures also because we are doing the same in the multiple load case optimization, but in a more simplistic manner. So that you can do it in hand. Yeah. So this name is given by you for the reference in the results, basically. You can give any name. This is the type of the analysis. It's a Kratos one because we can couple with other external solvers. So this is Kratos. You can couple with OpenFOAM, or at the moment we have tau coupling also. So you can run your basic primal analysis in other solvers. We don't care. Then Kratos is just an optimizer, not a structural solver. We don't care basically. So that's why the type is there. So you can write your own here also to couple with other softwares. So for this type, you have these settings. In here, we have a model part name, which is used by analysis. This is the structural mechanics analysis, as I told you. And here we say we get the settings from this JSON file, which I showed you earlier. To complete this analysis. Then this analysis, okay, fine. But you need to calculate the responses because optimization need a objective function response. And then how do you calculate the response? Because you can have multiple responses as in this case. First one is mass. So the type is mass response function. You just need a structure. Whatever the model part, you need to calculate mass on. Because mass is super straightforward. You can do direct sensitivity analysis. You don't need adjoints or this complicated stuff. Then you have the strain energy. For that, you actually don't need a joint, but just for the sake of saying, you can have a here's response which needs a joint also, like drag response. If you want to calculate drag values and reduce drag and do shape optimization or topology optimization. For strain energy, you don't exactly need a joint. I'm not going into details in that one also. Yeah. So these are the 2 responses. So these names are up to you, but they need to be unique always. Because you will see in the paraview, these names will pop up in the results. Yeah, then something comes like control. For that, I will use basically our documentation because we are a little bit proud that we have a little bit better documentation for optimization, but not perfect for sure. It can be like improved. Yeah, it takes time to open. That sucks. Huh? Sorry?
These applications, that's why they don't have support
No. I don't expect that also to be in the future also because it's super hard to make these settings in GID. It's a lot of effort. So it's easier to do it in JSON. That's why we have these block-wise structures to make in. And then we wrote a lot in here. If you go to applications, optimization application. Yeah. Some things are still missing, but it is a little bit better. At least something is better than nothing. Yeah, it takes time to load. Yeah, OOMs are always empty because I didn't have time to write OOMs. So you can go here, application and optimization application. But if you go for the other tabs, you will see information, like how the workflow. Why taking this much time? Yeah, so you have the workflow, like all of these steps which I explained now, it's there, a little bit more explanations. Yeah, but I will go into the concepts because that's most important one. So I think it should be here, the concept, the basic concept in optimization. Yeah, this is the image I was looking for. This is the basic concept of optimization. So in optimization, we have two different spaces. One we call the physical space. I will explain the difference. Other one we call the control space. The physical space is basically where your actual variables lie, like Young's modulus. They are actual physical variables in actual reality, or density. They are in the real world. That's why we call it physical. It's graspable, basically physically there. Then you have something called control space, which is basically a space where it's good for the optimizer. Why am I saying this? So the control space is basically are used in the algorithms of the optimizers so that they can find the better solutions in the physical space. Because whenever you calculate the physical space, let's say that your strain energy with respect to Young's modulus sensitivity, that's if you have a really maybe 100,000 elements, you have a super high noise there. So that sensitivity by default has noise. When you increase the dimensionality of your problem, the noise is super. So that if you are working with noisy sensitivities, then everything updates will be noisy. That means it's not feasible to manufacture anymore. To make it smoother, what we do is we use the smoothing operators or regularization operators, we say, which makes our algorithms to work in not in actually the physical space, in the control space, so that everything is smooth. So that's why we have different spaces. So your response function always works in the physical space because it needs to calculate mass that needs to be physical value. So that's what response function is. Then here response function basically gives J1 that can be mass, in here strain energy in our example. And it also gives gradients with respect to whatever the variable you want to calculate. In the case of shape, phi is basically the nodal positions. But they are super noisy. Then, yeah, forget about the response routine. It's an internal detail. So this is passed to something called control to translate these noisy sensitivities into the control space. So control is the guy who knows how to communicate between control and physical space, do back and forth mapping. So it can do back and forth mapping. Only control can do it, not even algorithm. Algorithm fully lives in control space, not even in physical space. Responses fully live in physical space. So that's this diagram is about. Yeah, so that's why the controls are there. So SIMP, I don't know how many of you know about topology optimization. SIMP is one of the ways you can do topology optimization. I cannot recall the longer name of SIMP. Yeah. Yeah. Right. So this says the control model part is structure. So that's where you control the basically Young's modulus and density to remove elements. Topology means removing elements and putting elements to have different structures. And here you say list of materials because we allow multiple material topology optimization. That means you can have list of materials in here and then ask topology optimizer to reduce my strain energy and give the basic structure. That means one way it will put aluminum, in other beam it will put steel, like that. You can do that kind of discrete material grading we call. Now we are working with continuous material grading also. That means for concrete. That's one of the other research areas which we are working on for concrete, so that you can actually manipulate Young's modulus by small amounts in concrete. Yeah. These are projections, a little bit advanced. So you can think of them as, okay. So at the end, you either need to say this beam is steel or aluminum, right? You cannot have 1 bar, half aluminum, half steel, which is not possible to manufacture. So to push that, we use this kind of projections. That's the purpose of projections. Yeah. And this is the filter, which I told you for smoothing. So how much is the filter radius? That means how much smoothing you will have basically in your domain. If you increase it, you will see that like you build up really thick ones. If you decrease it, you will see that it's becoming a little bit thinner but noisy. Also, the structures. This is about the control of how to do the mapping, because filtering defines the mapping. Actually, no, filtering and these two both, because it's projection. So once the control is defined, you can have multiple controls. That's why it's list, because we allow now shape, thickness, Poisson ratio, topology to be done at same point. So everything can be done at once concurrently. There are problems and merits of the way we are doing. Yeah. Then you have the algorithm. So the simplest algorithm is steepest descent, which we also have, but the problem is it doesn't allow constraints. This topology optimization problem has a constraint, which is basically the mass. Constraint is there, and we minimize the, here you see. So objective is to minimize the strain energy. Constraint is to mass. This is basically the 50% of the mass value. So at the end, what we want is 50% of the mass, but minimizing the strain energy as much as possible. That's this constraint optimization. So you can have multiple constraints, but only one objective, because we don't support at the moment multi-objective optimization. And we say the controls is simp, you can have multiple controls as a list. So this name is reflected in here also. You use the same name. And this is the line search. It's kind of like saying when you get the gradient, how much you go in that opposite direction of the gradient. What is the step size? How do you search how to go? That's called line search. So constant step means basically no line search. You just use this value, basically. Yeah, this is gradient norming. Basically, in norm, there are multiple ways. And this is the convergence criteria. So at the moment, I'm just running for 1e plus 4, 10,000 steps. No stopping. You can have multiple convergence criteria in here. There. You can combine the convergence criteria also, like having AND conditions and OR conditions. Everything is possible, but for simplicity, I didn't put them. Yeah. Then you rest of it is fine. So that is the algorithm settings. Then you have the processes. Just for outputting, basically we use the processes. You can, so these are also processes which can infiltrate the optimization algorithm as well as the structural problem. So you have two different levels. So it's nested. This is called in our lectures nested analysis and design, because your optimization is nested with the structural problem. Okay, this is nested analysis and design in the structural optimization 1 lecture. Yeah. So that's this. So let's see how we can run this. So I will open this in integrated terminal. So it's on onboarding. It will also not run because we need the optimization application. What is happening here? No, sorry, my mistake. We need to run not the main Kratos, basically. We need to run the optimization, because main Kratos is just copy pasting here. Right? You need to run the optimization analysis, not the main Kratos to run the primal analysis. My mistake. Yeah, it requires this basically. So I need to install that. Python -m pip install Kratos optimization. Yeah. Now you can run it. So it runs. See, yeah, it's a lot of output basically, but you get a summary file, which is in here. So you see. So this is the objective value, standardized objective value, because as we always only can do minimization, so we always standardize. If it is a maximization, we multiply by -1. This is the relative change of the objective, absolute change, and the standardized constraint value. We always standardize constraints also. And these are the actual values. This is strain energy value and the mass. This is mass analysis volume. Yeah. So these are the initial values. So you see here, so if you look at the absolute change, so it's positive, so it's not reducing because it didn't find a way to first reduce. So after some point only, it starts to reduce. Now it's reducing. So here now it's negative relative change, so it's reducing, but not exactly. This is absolute change, so it's positive. It's not negative. So relative change is negative. So this is here. So it's still running. You see, you can visualize the result. So you see here, there are a lot of variables now. Yeah, to visualize. So we can just look at Young's modulus change. So it starts with something like this. So it builds something like this yet. Still, it hasn't converged. Because this is a fixed, this is slip, this is sloped. So it builds an arch like this and then builds the other structures now. They're still emerging in the optimization. Here we can do 2D. And yeah. So if you just run it, so you see it's kind of, that's how the optimization works. So it builds these arches and then it builds other structures later. So this is the Young's modulus. So you can check actually how the sensitivity look like, as I told you. So let's see whether what I told is correct. So let's look at strain energy Young's modulus. You see, it's not so nice. So this is the D strain energy, which is the name given by you, the response function, and with respect to Young's modulus, D Young's modulus, and then you have D mass with respect to D density. Yeah, like this, it's a constant value. And then you have here basically D strain energy, D sim. That's actually your response with respect to the control. You see something like this. So you have a lot of things, and this is the search direction where the line search has found to go in this direction. Yeah. So the control field is there, which is in the control space. The control field, which I told you, yeah, it's not physically graspable. It's just for this regularization. We have the control field. Yeah, let's see how it goes. Yeah, so we load the new files. Yeah, you see, it builds the structure now, little by little. If you change the radius of this filter, like I have, I think 0.3, so you will see this getting thicker a little bit. So then the mass is a little bit higher for sure. Yeah, that's more one solution. So it builds the structure now. Yeah, it will run until 10,000 iterations, I think, because I don't have a convergence criteria. Yeah. Now it made the basic structure, so now it's reinforcing it now, basically. So it found the basic structure. Now it's reinforcing it. Yeah, that's basically regarding the optimization example. Yeah, you can just ask any questions about anything, basically. Yeah, if you have any, or you can play around with it and then let us know also. Yeah, for the Apple guys, I'm sorry. Yeah, so for the Apple, we have hard time actually, but I think within next month, we can find a solution for Apple guys also. But this time, yeah, it's not there yet. Yeah.
We can also like repeat the values of the objective function. This is also sort of right?
In the okay, so I didn't talk
always between strain energy.
So okay, the question is those are historical as per the optimization, but those are one value for the whole iteration. Mass is one value.
So it's not known.
Yeah, it's not nodal. Yeah. So because of that, in optimization, I didn't go into that detail because there's no time. Optimization has an additional data value container called problem data, which is used. That is what is printed in here. Whatever is in problem data is printed in here. It has a history. So that's why we used actually to put everything about optimization stuff, not the single physics stuff from the Kratos. Because that it needs anyways the history. If you run a transient optimization, you need to have a nodal history as well as optimization history on top of that. So it's nested, it's becoming complicated. That's why we have a separate container which links to the Kratos structures in optimization, which is we call problem data. So for that reason, we have separate output mechanisms for problem data. If you see here, so we call them here optimization problem. We call that data structure ASCII output. And then we have optimization problem VTU output for visualization. So we have specific output mechanisms for this exact container to store. So if you look at optimization application, I can show. I closed it. New window. Yeah, let's go to master. Yeah, so optimization application also has the same kind of things. So you have conditions, constitutive laws. Yeah, optimization application also physics agnostic. These constitutive laws are not meant to be physics based. These are for regularization because we can use physics intuition to regularize also. And yeah, that's why this constitutive laws, it's called Helmholtz basically. So for regularization, and then it has elements. So Helmholtz elements are there for regularization again. So regularization is a different research topic. It has a lot of advanced methods and still being researched. In here, you have optimization analysis. So this is the one which we now run because, and then in the first thing which it does is basically, it creates an optimization problem. This is the biggest container. Actually, it is bigger than model because optimization is on top of the Kratos. So this is bigger than model, basically. Model can be a subset of this also. That's how it is designed. And it can have, what do you call this? In the model part, I said, you cannot add solution step variables later point. You need to first say. But in optimization problem, we allow that. You can add values at a later point also if you see it. But the problem is output processors might ignore them because of the columns. Because it first calculates the columns, all right, then only write those columns. If it is not there when it calculates the number of columns, then it will not write. But you can use them in the calculations because this allows it. We allow it purposefully. Because these are basically per iteration, per model, one value, two values, or a field of sensitivities, not like nodal values. Yeah. Those things we still use Kratos. We never mix those. This is just for optimization data, like sensitivities. All those things we put in here. Yeah, so yeah, I didn't go into details of this because this will become a little bit complicated because of all the filtering and all those things. But if you're interested, you can always email us or go to the documentation because we put a little bit of effort on there. Yeah. With that, I conclude the workshop. Let's see the final result before concluding. I'm also interested. Now, 2000. Yeah, it's just reinforcing and pushing it to the boundaries because it's discrete material optimization. So it's pushing it to the 0 or the maximum value. It's two materials only. So it's pushing it now. That's what it does. It doesn't find new poles. It just pushes it to the extreme bounds of the existing poles. That's what is happening with the projection. After some time, it pushes it to either the top value, which is the steel, or nothing. There is 1 or 0 value at the end. You will end up only red or blue at the end. It will take some time, but it will end up with red or blue. Yeah. Yeah. From okay. this is the end of the Kratos workshop. Do you have any questions or any suggestions how to improve? Anything is welcome, basically. So this is the first time we did this. Yeah. Or is it too much for a day? Or too less? Also fine. We can put sort of more stuff less next time. No problem at all from our side. Yeah.
How much time do you think it would take to at least to get something running from the scratch?
Okay. Which type of running are you talking about?
Like anything to start.
If you follow the examples, if you run it without any changes, okay, I think the example should run it basically within 1 hour or something. But if you want to learn and then do it, I would say you need to, I cannot estimate a time frame because it's different for every person. I don't know, to be honest. Yeah, you need to dig in and then go to the jungle and then see. There's no other way. I don't know. Sorry. Can you give estimate? I don't know.
It depends.
It depends. It's super hard for us to say because we are so involved. For us, if you come up with a problem, okay, it might not take so much time to fix. But for newcomers, it's a totally different thing. We understand. That's why we are working so hard to make everything simpler. Like tensor adapters is a new concept which came like 3 months or 4 months back. So we are trying to improve to make everyone's life easier. Actually, also our life also easier then. And yeah, but it's still ongoing process. Yeah. So sorry, I cannot answer that question exactly. So any other questions or comments, feedback? Everything is welcome. Yeah.
How but faster way of doing this respect like this the result of the simulation.
Yeah.
So it would also work, for instance, if I want to break down the objection value.
Yes.
Okay.
Oh, I'm sorry. Objective values means
If I wanna like if I'm gonna look at the well effect maximization.
I mean, objective values are just scalars always.
Yeah.
So you don't need tensor adapters for that. They are just scalars always. Tensor adapters are there for basically high dimensional tensors. I mean, for the basically the primal one, it can be fluid structure. So you need tensor adapters to do manipulations. Like that's what optimization is doing. So you get this, okay. All of these basically are tensor adapters. That's why they don't have variable names because as I told you, in Kratos, variable names are always uppercase letters, big streaming letters. In here, you have strings. These are not variables in Kratos. These are tensor adapters which we store in the optimization problem so that the algorithms can use them because in optimization, all the algorithms are fully patterned. How do we make them efficient and MPI compatible? Is by using tensor adapters to do the operations on that and then write back and forth to Kratos and to NumPy. In here, we support SciPy algorithms also, as well as Pyro algorithms because of the tensor adapters, basically. Yeah. Any questions? Yeah. Okay, then. Thanks all for coming and attending. It was a nice pleasure for me actually to conduct this. Yeah. Then if you have future questions also when you are dealing with Kratos, just write to any one of us or write to Kratos repository in issues. So someone will answer for sure. Yeah, if you are not that open, you can write to us. No problem at all. Yeah. That's it then. Yeah. Good luck. Okay, I'm closing the call now. So see you then. Bye.